So in the previous class, we had started looking into the concept of incremental learning, especially the setup which we define incremental learning to be, and we had also briefly discussed the problem that a general deep learning model will face in an incremental learning setup, which is the problem of catastrophic forgetting. That was basically that when you train on a set of classes and then you get a new set of classes to train on without maybe access to sufficient data from the previously seen classes, on training on the new classes, you'll start losing information about the previously seen classes, and your performance for those previous classes will start falling. And this phenomena is also known as catastrophic forgetting. So we'll start to look at some approaches. I mean, we'll cover two very basic approaches for dealing with catastrophic forgetting in an incremental learning setup. But for that, one concept that will be used regularly is the concept of knowledge distillation, which we had also started to discuss in the previous class. And this process is basically a process of transferring knowledge from a pre-trained teacher model to a student model. And the original objective was, I mean, at least one of the original objective was to train a smaller models with help of a larger model that was pre-trained on some very, say, large data set. And suppose you wanted a smaller model which has low computational requirements. So knowledge distillation provided a way to transfer the knowledge of your larger and maybe much more better generalized and better trained model to a, say, a smaller model. Okay. And in such case, the assumption is that the child model is generally your smaller model. The other situation that we had also discussed was the case of a self-distillation, where there is no decrease in at least the size of the models between the teacher and the student models. But this simple distillation was also seen to be uh, helping the performance improvement of the same architecture, but while using, say, a teacher model to guide the training process. We'll see how to basically perform such a training. The idea is that when you are basically training, so you have trained a teacher model and you want to now train a student model, you want to make the student model produce an output that is roughly same as what the teacher model is producing. So when I say the output, I just don't mean the best class that has been predicted. I want all the distribution, the entire distribution of the prediction. Say, for example, if you have 4 classes, so the teacher model produces the probabilities in this way. One of them, say, 2 is the class that for which gets the highest probability. Others have some different, but say lower probabilities. The student also should try to emulate this thing. The student may be producing something like this, okay, but the student also should ideally follow the teacher and produce a similar output. So rather than a single target of, say, predicting 2, the student is given an additional target of following the or predicting the probabilities of all the classes as the same as what the teacher was doing. So you no longer have a fixed target or a single hard label. I mean, you have that, but apart from that, you also have a soft label that you also want to follow. And it's been observed that by using this process, you are actually able to transfer a good amount of this discriminative power or predicting power of the teacher into, say, a smaller student network. Or in case of, say, self-distillation, you are able to improve the discriminative power of the student network. Even though they have the same architecture, the student network starts performing at the end of the training, performing better than your teacher network. And so for your student, you will have 2 types of losses. We'll have the standard classification loss, for which you are basically trying to match the prediction with the hard true label. Your true label, say, I say there are 4 classes and your class is basically 2. So you will get a one hot vector. When I say one hot, it means that it will have only a single one and the other values are 0. So if there are 4 classes, only the say in this case, if you have 0, 1, 2, 3, 4, you, in terms of starting from 0, you will have 0, 1, 2, 3 as the labels. So this particular position will be 1 and the other position will be 0. That's how your hard label will look like, whereas your soft label will have the entire set of, say, whatever prediction your teacher is making. So if it's, say, 0.2 and your 0.6 and then your 0.1, 0.1. So that's the difference between a hard and soft label. Okay. And we also said that we'll be discussing some type of losses that's being used in noise distillation. One of them, a very popular one of them, is the KL divergence loss. And we'll see how to basically extract this particular loss from your given outputs. Now, the first step obviously has to, you need a pre-trained teacher, so you have to train your teacher model. So we are doing it for classification, so let's train it using a cross entropy loss. That's sort of a standard in, say, any sort of a classification setup. And suppose for a given image X, the teacher model produces the particular this as an output. So your last layer produces this output. This is generally refers to as logits, the last layer output of your any network. And we need to train this model using cross entropy loss. So this first of all has to convert it into probability. So that we can apply your cross entropy loss. So in order to apply, convert this into probability, we'll be using the softmax function. And your softmax function looks something like this, where these are, say, suppose these are, say, 2, 4, and 5 are the three outputs that was being produced. And suppose it's a 3-class classification problem. You will raise them by exponents and divide them by the sum of the exponents of all the values. So you have this particular case, you will have this particular setup, you'll have e square divided by e square plus e to the power 4 plus e to the power 0.5. And similarly, based on which position you're dealing with, the numerator basically changes. Okay, and this particular setup will give you a value. All of these these values will be between 0 and 1, and the sum of these values will add up to your 1. Okay. So this is the probabilities that you get from your given output or logics that you have. Okay. Now, based on this, you can actually extract the cross entropy loss, and which is very straightforward. The cross entropy loss is basically the summation of your ground truth probability for a given class and the predicted probability for a given class. Okay. But remember, for simple classification training, our ground truth basically looks like this. So if the class to be predicted is 1, say this particular class 0, 1, 2, then your ground truth prediction will basically look something like this. So for all the incorrect classes, you will have 0, and for the correct class, we have 1. So this particular expression will actually reduce to a single term, because the summation, even if you do summation, you get multiply 0 with the other two terms. So this gets reduced to simply minus L and P out of the, say, your correct class, in which case this is, say, this is class of 1. Please note, this is not the probability one, this is the class. I'm referring to the class as one. So I can even refer to this as C or C. Right? And once you do that, this is your cross entropy loss, and your model will try to minimize this particular loss. And with effect, what we will try to do is that it will try to increase the this particular prediction probability of your output rates. It will try to take it to 1. So because you're trying to minimize this thing, so this entire thing starts getting maximized, and the probability of your correct class will, with sufficient training, will move closer and closer towards 1. Okay, and that may be at least the case for your training samples. There's no guarantee that this will be you will get very close to 1 for all test images. That's never the guarantee. But at least for training setup, it helps your model to at least identify some of these classes, or at least give higher probability for the correct class compared to the other classes. And this is, I think, pretty standard. You have done this for basic classification training. This is a very standard setup. Okay. Right? So you have a certain cross entropy loss. You train your model using that cross entropy loss, and at the end of that training process, your teacher network is now trained. And now I'll freeze this model basically and use this as a teacher model. And then I have to train a student model, which will use your standard classification loss, but also a knowledge distillation loss from your pre-trained teacher model. Okay, so you have frozen the teacher model. You are now training your student model using two losses now: standard cross entropy loss for the classification setup training based on the hard label or true label, and your knowledge distillation loss based on the soft labels or the predictions of your teacher network, which you want to match. Okay, so again, let's see the examples for this. So suppose your student model has taken an image X and has produced this particular output. The logits are, say, 2.5, 1.5, and 1. I need to again convert it into probabilities. So I'll basically use the softmax function again. And I'll end up with some probabilities which are between 0 and 1. And if you add these three, you get basically 1. So fine, we have our probabilities for our student model prediction as well. We calculate the cross entropy loss, which is basically the same as what we have seen before. Even if you have your summation over, say, the product of your ground truth probability and the predicted probability, since this will be using a hard label, and suppose this has one only for the class 1 and the others will be 0. So effectively, this will reduce to a single term where you have minus natural logarithm of the predicted probability for the correct class. Right? So, but we still left with another loss, which is the knowledge distillation loss, which we'll see what to do about. Now, the knowledge distillation loss will be calculated between the teacher's softened predictions. We'll come to what softened predictions mean, and the teach students softened predictions. Okay. Suppose for that same input x, for which you just got a set of output variables, output logits, you pass it to the frozen teacher as well, which cannot be trained at this stage, but at least you can use it to extract this outputs. The teacher produces a logit of 4, 2, and 0.5, whereas the student produces the logit of 2.5, 1.5, and 1. And remember, the objective is that your student not only predicts the correct class with a very high probability, but also matches the output produced by the teacher. Okay, at least if not the exact output, but when you calculate the probabilities, at least the probabilities should match of the not incorrect classes as well. So in a way, you are also learning how the classes are related to each other whenever you get an image. So this relation cannot be extracted from a hard label, which is basically ones and zeros, ones for the correct class and 0 for everything else, but can be extracted from your teacher's predictions, which is available here. So in a way, you're providing some additional information about relations between the classes as well. So say suppose in this case, the true label class is 1, which is say in this case, the index 0. Okay. And as you can see, at least if I simply use this for prediction, at least the student and teacher are both predicting the correct class. But still, I want to match the incorrect classes also, somehow at least the probability distribution among these classes with the teacher. Okay. So you'll convert them into probabilities using softmax, but with a difference. We'll be using something known as a temperature, which is nothing but a factor that basically divides your logits that you have provided. We'll discuss in the next slide what is the utility of this temperature parameter. But let's for now consider that you're performing softmax, but before applying softmax, you're dividing the logits by a value, say some value, say 2 or 3 or whatever, greater than 1, something greater than 1. Okay, right. So with this, the softened logits of teacher and student are as follows. You're basically dividing by 2. So these are the resulting softened logits. Okay. Now, obviously, this distribution needs to convert it into, say, this set of values need to be converted into probabilities for both the teacher as well as the student. So that is what we do. We use the softened logits and pass it to your softmax operation. And your softmax operation or function basically produces these probabilities. Okay, one for your teacher, one for your student. As you can see, for both these cases, you have the models are correctly predicting the correct class, but the probability is very different. Okay, and so that is what we want to match. We want to match the entire probability distribution for the correct class as well as the incorrect classes. In a way, we are transferring the knowledge about the information or relation between these classes. Okay. So what we do, there's something known as a Kale divergence loss or a Kullback-Leibler loss, which is the most popular loss that is used for knowledge distribution. And at the core of it, the core equation is simply this. So you have your predicted probabilities for classes of, say, given by the teacher and the student. You simply make this calculation for every class. So for, say, the first class, you take the predicted probability of the teacher and you multiply it with the log of the predicted probability of the teacher by the predicted probability of the student. Okay. And this is something similar. You have both the logits, the probabilities, and then you basically make this particular calculation. Ideally, if both of these predictions are exactly the same, both the probabilities by the teacher and the student are the same, KL divergence loss will be basically be equal to zero. And that is your target. You want to reduce the KL divergence loss to zero. And yeah, if in fact you can check this in this particular part of this equation as well. Suppose if these two values were the same, then you would have had ln natural logarithm 1 or say log of 1. And whatever may the value that is getting multiplied over here will not matter because log of 1 is always 0. So if these two probabilities were exactly the same, you would end up with 0, which is what the KL divergence is supposed to give you. KL divergence is supposed to give you 0 if both the probability distributions are basically the same. Okay. And this is how you basically perform knowledge distillation. You want to make the output of your student the same as at least the predicted probabilities by your student the same as whatever the prediction the teacher is giving. Okay. And that's why you're using the KL divergence loss, which basically finds out whether two distributions are same as each other or not, or whether it's a difference between them. Okay. And that's the goal of knowledge distillation. And for knowledge distillation, as we have seen, that your teacher gets trained only using a standard classification loss, whereas your student gets trained using a standard classification loss as well as a knowledge distillation loss using say KL divergence. Okay. Right. So when you're training your loss, training a student model, you might combine both these losses equally. Maybe you give equal importance to both. But these are hyperparameters. So maybe while training on a particular data, you find that giving higher probability to KL might help you give better results, or maybe giving higher weights to your cross entropy loss gives you higher results. So that will depend on your cross validation and other setups that you use to basically determine the hyperparameters. Okay. Let's come to the concept that why are we using the temperature? Remember, the whole point was basically matching the go back, basically matching the probability distribution. We could have simply applied KL divergence to these without having to reduce or maybe divide these values by some temperature. So why do we use temperature? So the use of temperature is actually for a very interesting purpose, you can say. Generally, when you are training any say teacher model, only any model using only say hard targets. So initially, when you have trained your teacher, you would have been using only hard targets only. Your models might get at least for your training samples, it might get promoted towards giving very high probability for the correct class and extremely low probability for the other classes. So if that's the case, when you find out the probabilities for them, the whole point of forcing the student to produce the same output as the teacher was to also learn the interrelationship between these classes. But if these probabilities are too low, your knowledge distillation loss for at least these predictions will not affect your overall training purpose too much. Okay. So generally what we do is that we use a temperature T that is greater than 1 to reduce these values by some factor. Okay. And then we calculate the probabilities. And what it does is that it ensures that the probabilities of the non-maximum classes or the incorrect classes are not negligible. Okay. Not necessarily the incorrect classes. If your model is making the incorrect predictions, also for the other classes, the predicted probabilities are basically not negligible. That you're ensuring is by reducing the overall scale of all the values over here. If you can do that, you can test it out by writing a simple equation as well. And I have done an example for that over here. So if you do that, the other probabilities are not negligible. And as a result, you can still capture some relationship information between them. So in this particular setup, say, if you can look at it, the teacher probabilities with say temperature 2 will be something like this: 0.64, 0.23, 0.1127. Student 1 is 0.48, 0.29, 0.2272. Whereas if you are not using temperature, or basically temperature equals to 1, which is basically an identity sort of setup, then you'll get teacher probabilities as say 0.85, 0.11, 0.02, and student probabilities as 0.62, 0.23, and 0.14. And then what happens is that since for your teacher, one of the prediction probabilities is extremely high, the contribution of these two will become very low for your knowledge distillation loss. And therefore, again, even through this loss, your student will start focusing only on the best prediction, which is not the goal. You're trying to learn the entire distribution and transfer the entire distribution to your student, right? So I think, yeah, with this, we're done with the concept of knowledge distillation. Any doubts up to this point? We'll start with the incremental learning methods after this.
So, sir, we divide both teacher and student probabilities with temperature or just with teacher?
No, no, no. Both with the same temperature value.
Then,
Otherwise, not be fair. Hello.
yes, sir, I got it.
Okay. Okay. So let's start with the next topic, which is we'll look at
Sir, is
very
there any
basic.
sir, is there any ideal values for temperature?
No, no,
You have
this again is
taken
a
two.
hyperparameter. So
Okay, okay.
I think I have seen people use 2, 4, but then it will depend on the data set, and it's a hyperparameter, so you can tune it. So,
Actually, in ChatGPT also for API, we are providing some kind of temperature equivalent, some value. If it is
okay.
more, then the ChatGPT will give the more sensitive, more creative answers actually. If the
Okay.
temperature is less, then it will give the normal predictions,
More
normal.
confident predictions. Huh.
Yeah, yeah. Is there any relation with this temperature?
Uh,
Temperature? I don't know.
Internally, I'm not sure, but the idea is still the same.
Okay, okay.
Internally, I'm not sure exactly what's the utility over there,
There,
but the
the
idea is still
temperature
the same.
value ranges from 0 to 1 actually. If the value is increasing, then the model will give the more creative answers actually.
Okay.
So I
So I
just
think
want to
something
map.
similar is here also. If you use a very high temperature,
Yeah,
you
yeah.
will be able to, any sort of say LLM models. The next word prediction depends on the probabilities of these next words. So if you're using maybe, I'm just thinking about it. If you're using something that makes these probabilities roughly close to each other, then you can also come up with very, say, not so obvious answers to your questions. So maybe that's the case, but I'm not sure of the exact set.
Thank you, sir.
Okay. Let's move on to the most basic way of performing incremental learning, which is learning without forgetting. And we'll be using especially your knowledge distillation loss for this particular purpose. Okay. It's a very famous paper from ECCV 2016. And the good thing about this is that it does not require training samples from your previous tasks or previously seen classes. The idea behind this is basically utilizing knowledge distillation to preserve the output of your model. So how we do that? So first we train a model on the first task using your general classification laws, and there is no difference as it is. And once you're done with your first task, you simply save it as a previous model. So you don't discard the model, or maybe do not override that model. You keep it separately as a previous model. Okay. And for the second task, you will utilize, whenever you have trained on your first task, you have your same model M1. What you do is that you also store a copy of it as a previous model, and you go on to train M1 on the second task. Okay, say task 2. But while training on task 2, you will be using two losses. One of the loss will be a standard classification loss for your new classes that you have over here, say C3 and C4. Okay. But the other loss will be a knowledge distillation loss between the output of your previous model and the output of your, say, whatever model you're training now, this particular setup, whatever model you're training now. Okay. And obviously, there's one big problem while you're while you're calculating a loss between the prediction of your previous model and your current model. Can anyone say what is the problem with this particular setup? You have your model previous, which was trained on your previous task, and you have your current model, which was trained on your, which is getting trained on your current class. So if I try to take the outputs of these two model and build a loss on top of it, will there be any problem as such? Suppose you have already seen maybe say 10 classes up to now, and your M2, the new task is say M3 is giving you another 5 classes. So what is the problem that will happen if I try to directly find a loss between them?
Losses may be more high or more low, extremely
No,
high.
no. See, the problem that the losses will come to the losses, but the problem is that the output size of MP is 10, whereas the output size of M3 will be 15. So the output size don't match. You had previously only 10 classes, now you have 15 classes. So if I try to directly find a loss between these two outputs, you'll not have a one-to-one matching between the outputs, right? You have at least 5 outputs in the new case for which there is no corresponding value in the old model. Okay, so that will be a problem, and we'll see how to deal with that problem. Okay, right. What We'll come to this why once we're discussing this thing, and we'll see what we are doing to ensure basically your model does not forget your previously seen classes. So while training your new task, so your original model is basically same. It has seen a set of say classes and it knows how to predict say 10 classes outputs for 10 classes, and now you have given 5 more classes to train. What you do in learning without forgetting is that you train this new 5 classes output for and you don't have access to previous class images, so you only have access to the this 5 class images in this particular setup. So what you do is that for this 5 class, you take the training data and use your standard cross entropy loss to train for classification. Okay, but you have also saved your previous model and you have this particular model. So what you do is that for the same set of images of these 5 new classes, you ensure that the previous outputs of your model, that is the previous class outputs of your current model, exactly matches with the previous these outputs of your preserved previous model. So for example, you have 10 plus 5 in your output in your current model, and your previous model you had an output of 10. You apply a cross entropy loss for your current classes, but for the same image, you ensure that this first 10 values of your output exactly matches with the first 10 values of your previous model using knowledge distillation. Okay, this is something we have been doing in knowledge distillation. We have been just seeing in knowledge distillation. We don't allow we force a student model to exactly map towards the prediction of your teacher model. Here we are doing something similar, but only for those set of outputs for which we have a previous value available. Okay, let me again rephrase this. You have your previous model, say M1, that was trained, M2 maybe. We have already trained M1. Let's go a bit ahead. M1 where you had 5 classes, M2 where you added 5 classes, so you became 5 plus 5, 10. And now you're currently at M3, where you have total of 10 plus 5 classes, total 15 classes. So your output size also varies. For your immediately previous network, which is M2, you have an output size of 10. And for this particular network, you have an output size of 15. So, and you don't have access to training data from here. So you only have data of the current task. So what do you do for any given image? You pass it through your model, M3 model that you're training, and you use the classification loss or the ground truth to basically classify these 5 classes correctly. Okay, but for the remaining say 10 outputs for which you don't have correct data, what you do is that you map the same image, but you try to match the output of this say first 10 values of your outputs with the value that is predicted by your previously saved model using the same input. Okay, any doubts in this matter?
So, sir, is it like we just copy paste the previous 10 laws, or we like
No, we
calculate?
apply the knowledge distillation loss.
Okay.
That's why we study the KLD loss, KL damages loss. So for this portion, we are using the cross entropy loss. So the target of this portion is basically the new task ground truth, or the new task, whatever the output, the predicted, the ground truth labels are. But for the rest of the output, the target is the previous model's output for the same image, because we don't have any other image. We only have the new task images only. So for the same image, this portion goes, for this particular portion, we try to predict the correct class. But for this particular output, we try to predict the same value as the teacher model was predicting. Okay. So within the same, say, output vector, we have two different targets for different sections of your output. And what it does basically is that since you're preventing this particular set of values for your that which corresponds to previously seen classes from not changing, in a way you're ensuring that at least some of the knowledge about the previous classes still gets preserved. Okay. So now if I give you an old class image for
You mean that
testing,
like not forgetting means without forgetting means what? Because of we are holding the previous information, right?
so you're talking
Hello.
about the title without forgetting.
Yeah, yeah. Yes, yes.
Yes, yes. So remember, the incremental learning has one core problem, that is catastrophic forgetting. So the name of this method is learning without forgetting. This is a paper which is called learning without forgetting. So you're trying to
Hmm.
reduce the forgetting levels, and
Because
for
we are
that,
preserving the previous information as input, or sorry, as output. That's why we are asked it as a without forgetting, right? I want to
yes, yes,
understand like why we are saying this as a without forgetting.
you're trying to
You mean
prevent the problem of forgetting in an incremental learning setup. That's why it's called without forgetting.
mm-hmm.
Okay. So in this particular setup, if as you can see, there will be two specific losses. Again, you will have your cross entropy loss as well as your KL divergence loss or knowledge relation loss. But where you apply these losses will be now slightly different. Your cross entropy loss gets applied to your, say, new classes, what your output you're getting. But your for the same input, you're also applying the KL divergence loss between the output of your current model and your previous model. And you'll be using these two losses to then train on your new model. And this has been shown to be at least a very cheap way of performing your incremental learning, which does not involve maybe it will not require you to add maybe more sections or more parameters at every time. Only your final classification layer increases, which anyways has to increase. And it also does not require you to store any samples from your previous classes. That way your model size or say your storage requirement also does not increase over time. So in this way, it's a very cheap way or performing this incremental learning while giving you good enough standard results on incremental. It will obviously not be able to fully solve this problem, but it's a very initial method and it was found to be very effective research.
Sir, one quick question.
Yeah.
Uh, So let's say when we are in the model 3, right? So we calculate two different losses. Like one is the cross entropy loss for the current set of images that we are training, and we
Uh-huh.
back propagate that. And
Yeah.
then again we calculate the uh, PD loss, and then also we back propagate. So we are doing two backward pass in.
No. Basically, what you'll end up doing is you will add the KD loss and the cross entropy loss and backprop together
Okay.
because you're doing it for the same input. It's not that you don't have data from the previous classes, no. So you only have data from the current set of classes. Say you had, easier set of doing is that you had say two classes initially, then you added two more classes, and now in M3 you have 5 and 6. Okay, you only have images from classes 5 and 6. So for these images only we calculate the cross entropy loss as well as the KD loss, and we add these two losses and backward. We
So
don't
like,
have access to the previous class images.
so won't this like impact negatively the the classification for the current classes? Like we're
It
also
will.
back.
It will. I mean, it will. I mean, I'll. It will also then you'll have to also determine how much weightage to give to knowledge distillation, because the whole point is that you don't want your network to be fully biased towards the new two classes that has come in. You want to retain information about the previous classes, so there it will take some hit into the performance. That is obvious. I mean, I mean, I mean, as a newcomer, it might be not obvious to you, but it will. This problem will happen because you are making a trade-off between, say, ensuring that the current class performs excellently and but forgetting your previous C classes, but you're in this particular setup you're trying to ensure that your current class also performs reasonably well, or also you're not forgetting too much about the previous class. But then you can obviously, based on requirement, you can also control the knowledge distillation factor as well with some weightage. So you can, if you feel that in your current data set you are working well, or even with a very low contribution from KD, then you can reduce the value of KD. It's a hyperparameter, so you can basically tune it as per your requirements.
Okay.
Okay. Okay. So this is one basic method. Let's come to another basic method, that is iCard. And you will see that it simply builds on top of your LWF concepts, learning without forgetting concept. Right. So one thing that we have not done till yet is to save some examples from your previously seen classes. I mean, that is the, I mean, very naive way of maybe averting or reducing catastrophic forgetting. And that is what iCal does. But it is not as naive as it sounds, because choosing which samples to save, because you'll have limited storage space only, is also a very tricky job, which for which also iCal provides a method for. Okay. So the idea behind iCal is you'll have to save some of the most representative images of these classes that you have previously seen. And when you're training on a new class, new set of classes, you include these images into your current data set of when you're training on your data. So in a way, it's a setup where you might have a lot of data for, say, your new classes, C3, C4, but you also have some, at least some values from your previously seen classes. Okay. So you're not in a setup anymore where you have no data from your previous classes, which would be a very difficult setup for you to then prevent catastrophic forgetting for C1 and C2. But we have at least some data, so you'll be able to better maybe retain the performance of C1 and C2. We'll see how to do that, because still it's not very straightforward, because since C3 and C4 will have a large amount of data and C1 and C2 will have very less data, your model will still get biased towards C3 and C4. So we'll see how your iCal basically prevents this particular setup. Okay, there will be three main components of iCal. One will be your nearest mean of exemplars, which is something similar to, say, prototypes that we saw in few short learning. So we'll perform classification based on such nearest class mean or nearest means of exemplars. The next thing that is very important, because in this case we'll have some fixed storage. Say, I'll say that you can only store, say, 200 samples. So maybe you have first seen two classes. So initially you will store, say, 100 from first class, 100 from another class. But now in the second task, you see another two classes. So total classes you have now 4. So you'll equally divide the space among these 4 classes. So you'll have 50 per class. But then which 50 to discard from the previous classes? So these decisions will become tricky. And you always want to retain the most useful examples and discard the less useful examples. So that's what there's a herding strategy which is proposed by iCal, which will be seen shortly. And finally, we'll perform representation learning using your knowledge distillation and prototype rehearsal. We'll see, I mean, how to basically utilize this thing. The code ideas will still remain that you will now have data from all the classes, including the older classes. So you will perform your simple classification, as well as you will perform a knowledge distillation to prevent the outputs of your previous classes from chaining, similar to, say, LW. The architecture for this particular network will consist of a feature extractor, and it will also be followed by a single classification layer with as many output nodes as the class. So if you have 10 classes till now, the classification layer will have output size of 10. If you have 15, after adding 5 more classes, the output size will be 15, which is something similar to what we are seeing in, say, any incremental learning setting, where your number of classes will increase as the as you keep on seeing more classes. Okay, the first thing that we look at is the nearest mean of exemplars classification. Okay, so remember, we had seen something similar in few shot learning. The idea is that for every class, what you do is that you have a set of exemplars that you're saving. So based on these saved exemplars, you will take an average feature, and that average feature will serve as your prototype. And when you want to perform classification, simply whichever is the nearest prototype, you take an L2 distance or some other distance from your query feature to your each of these class prototypes. Whichever is the closest will be your predicted class. Okay, And keep one thing in mind, that whenever we are trying to do nearest mean of exemplar classification, the average will not be computed on the entire data that is available for any given class, because especially for your previously seen classes, you anyways don't have access to the entire data. You only have a few saved examples. So you will take the average of only those saved examples for that particular class, and you will come up with a prototype vector for that class. Okay, and then you can perform nearest try to find out the nearest class based on this distance. Okay. Right. So, and that's the idea. I mean, you'll predict basically that class level for which the prototype is the closest to your, say, test image. That's okay. And therefore, the question then comes up: then why are you not using your true class mean prototype? Okay. And the problem lies is that in the point that once you have moved ahead, say you're at task 1, then you move to task 2, you don't have the entire data available. So suppose I calculated a prototype over here, and after that my model underwent some training. Will this prototype will be valid anymore? Your model has changed at this particular setup, so your old prototype is no longer valid. You have to recalculate the prototype. If I now have to recalculate the prototype, I need access. If I was using the entire data, I would require access to the entire samples from airplane and automobile, which I no longer have. Okay. So what we have are exemplars at least. So I may have say 50-50 exemplars from airplane and mobile. So I'll always calculate the prototype based on these exemplars that I have for all of the classes, instead of using the full class mean, because that is anyways will not be useful for us. Okay. So we'll be using an average over the flexible number of, say, exemplars that we have chosen to get a good approximation of the class mean. And this is a very important term. We need to choose exemplars such that we always get a very good approximation of your actual class mean. Okay, and that's where your choice of exemplars or the process of selecting exemplars becomes important. Okay. The next point is representation learning within this setup. So you have your exemplars with you. At least we have not seen how to select the exemplars. That will be the next slide. But you have your exemplars with you, and you want to now train your model on any given task. Okay. So the first thing that iCal will do is to construct an augmented training set. It will contain the training examples from the current set of classes, and it will also contain the stored exemplars from the previous classes. Okay. And the training will, I think, it will still be somewhat similar to what you're doing in LWF. You'll be using some classification laws as well as you'll be using a distillation laws. Okay. So what you do is that your current network will be trained. So your current network, you will append one fully connected classification layer that will have as many classes as we have seen up till this point. Okay. So you have your feature extractor as usual, and you have your classification layer that has, say, initially previous classes were 10, now you have, say, 5 more classes, so total of 15. Okay. Now at least the training portion, you will be using this fully connected layer and using your say cross entropy laws, and later on we'll discard this and start using your nearest class mean classifier, which we saw in the previous slide. So the first thing that you will do is that you will do a correct class prediction, and to do so it will require some sort of a classification loss. So we'll use maybe, say, cross entropy loss for this correct class prediction, and it will again use similar to, say, your LWF. It will have a previous class, previous model, which has seen up to 10 classes, and it will apply your knowledge distillation loss between these two segments. Okay, right. There is now a major difference, however, from LWF. In LWF, in your new task, you only had access to your, say, current data set and not the previously seen data set. But in this particular setup, you have access to the current data set as well as exemplars from your first and second tasks as well. Okay. So it's no longer a case where you don't have access to any data from previous class. You have some data at least. Okay. And on top of that, you're applying the concepts of your losses of classification loss as well as your distillation loss. Right. So once this particular portion has been trained for a given task, you will discard the fully connected layer, and for predictions after that task, you can simply use a nearest class mean. Okay, NCM classifier, and or based on the exemplars that you have. Okay. and you'll be able to make a predictions, and turns out that it performs extremely well, even better than LWF, because you're actually preserving some of the uh, data points from the previous classes. But obviously, when you're preserving some data, there might be a scalability issue. So generally, iCal sets a upper limit on the number of samples that you set. Say if you set an upper limit of say 2,000 samples. So when you see the first 5 class, and you move to the next 5 class, you will maybe store say 400 samples per class. But again, when you see the next 5 class, now you have total of 10 classes. So every class will only now have say 200 samples. And as you see more and more classes, the number of saved examples per class keeps on reducing. But for that, obviously, there are two things has to happen. One, the first thing is that when you select exemplars, they have to be extremely good. They should help us in correctly estimating the actual class mean. And the second thing that is required is that they should have some priority with them, so that when we have to reduce the uh, number of stored examples for any given class, we should be able to easily remove the less important ones. Okay, these two things have to happen. Okay, and that is where your exemplar management comes into play. So whenever you get some new classes based on the new task that you get, it will have to your setup has to update the exemplar set that you have. Okay, since all classes are treated equally, whenever say T classes have been observed up to this point, and say you say that K is the overall restriction on the number of exemplars that you can store, you will equally divide that space for all the classes. Okay. So if you have T classes and you have total of say K examples that you can save, so for every class you will only store K by T examples. Okay. Right? So with this, that you are fixing the overall storage requirement, and you're not, so you'll not face any scalability issues. But for this to work, you'll have to be very careful about which exemplars you choose to keep and which exemplars you choose to discard. Okay. So for exemplar selection, they basically proposed a very simple strategy, because the goal was that you need to, whenever you're using any exemplars, the final goal is to come up with a class mean for that particular class, and the class mean based on your exemplar should be as close as possible to the actual mean when you use the entire data. So at each step of exemplar selection, you will select the next best example. Okay, that causes the average feature vector over the exemplars that you have to be closest to the average feature vector over all the training examples. Okay, so say first consider task 1. Okay, there is no incremental that is happening up to this point. You have say 5 classes and you finished training on class 1. Now you will be transitioning to task 2. So before that, I need to store some of the most representative samples from my task 1. So what do? I find the actual mean for each of these classes, because at least for task 1, I have the actual mean for all the classes. And initially I choose, say for any given class, I choose the sample which is closest to the actual mean. Okay. I choose one sample that is closest to the actual mean. Now, what I do next is that I have to choose another sample in the next iteration. So I choose one such sample such that this average of the first and second sample is closest to the actual mean. Okay. With that, I have now chosen 2 samples. Now I choose the third one. So I'll choose in such a way that the average of these 3 samples is closest to the actual mean. In this way, you are actually preparing a priority list of good samples for each class. Okay. And so on forward till you reach the limit, say M, that is allowed for every class up to that point. Okay. Similarly, you do this for all the classes that you have. Okay. And since you have chosen these in a manner where the most useful samples are actually higher up the list and the lesser useful samples are lower down the list, so we'll see that this will help us in deleting exemplars also, when you have to basically reduce the exemplars of any given class. Okay, so suppose you have seen this particular setup for task 1. Now you move to task 2. You have done training for task 2. Now you have to finally go to task 3. Now what will happen is that you have a fixed storage of say 2000 samples. Currently 50% of them are being used by the 2 classes in the first task. Okay, so you have 1000 of 1 and 1000 of 2. So if you have say 2 classes at this stage. Now you in task 2, you have come up with 2 more classes, 3 and 4. So total for class storage space is 2000. So every class only gets 500 samples. So for 3 and 4, we'll select 500 samples each. Okay. But for 1 and 2, I have 1000 samples. So there should be a strategy by which I should delete half of these samples from 1 and 2 so that the total storage is still 2000. Okay. So that is where your exemplar removal comes into play. Okay. Since as I just mentioned, that when you're storing your exemplars, you're storing the most useful exemplars first. So at some point, suppose I tell you that I only have space left for 3 samples, I can simply discard everything after the first 3 samples. Okay, because I already know that the first 3 samples are the most useful ones for that given class. Okay, and that's generally the idea behind exemplar removal. Okay. So if you have to discard a few samples, you take the first set of samples that are up to the size that you're allowed to keep right now and discard the rest of the samples. Okay, and this will still work fine because you have been storing the exemplars in order of their usefulness, right? And this is in general, this is known as the herding strategy of exemplar management. So exemplar selection or exemplar removal, you're doing it with some sort of herding strategy. Any doubts up to this point in exemplar management?
Is there a formula to calculate exemplar, or it's just like you get it and you store it as an exemplar?
No. See, exemplars are basically your training images that you're storing. So suppose if you have in your first task, if you have say two classes only, and you have say 1000 training samples from each, and you need to store only say 50 samples from each of these classes. Suppose the total space allowed is 100. So what you do is that for this, once you do this after you have done training for 1 and 2. So for this 1000 samples, you can use the train feature extractor to get the features, and using the features of all the samples, you can come up with a class mean for class 1. Okay, but this will be the actual mean because you have used all the 1000 samples. Now what you do is that you have to choose 50 among these 100, 1000. So the first sample that you choose will be closest in the feature space to your actual mean. Okay, so now you have your first sample from class 1. The next sample that you choose will be chosen in such a way that if you take an average between the first and second sample, the average will be the closest to the class mean. Okay, you can have multiple options at this stage, but the average of one of them will be closest to your class mean, actual mean. So now you have your second example. Similarly, you choose your third example such that the average of all 3 samples is the closest to your class mean. So you go on up to you reach your target of 50 samples for class 1, and you repeat the same thing for 50 samples for class 2. Okay, so that's the general idea. This, I mean, equation wise, I'm not sure what you're asking for.
No,
Is this clear?
Yes, sir.
Okay. Okay. Let's move to the next slide. Right. So there are, I mean, this was generally the idea about iCal, and you will see that most of even the recent methods use some version of this iCal and LWF concepts or knowledge relation or exemplar storage concepts, and have built on top of those. But these are the most basic ideas behind your say incremental learning setup. Generally, you have 2 ways of storing samples. Either you fix the number of samples per class, but then your overall store keeps on increasing, or you can the more common setting is to basically fix the overall storage space, and as and when you see new classes, the amount of storage available for each class reduces, which again, obviously, if you at some point maybe you'll not have enough data for any of the classes, so when there are trade-offs for both these approaches. Okay. But it's a very useful setup, and both iCal and LWF have been instrumental in I mean inspiring a lot of research in incremental learning. Okay. So with this, we come to the next topic, which will say briefly discuss the idea about, that's the concept of multitask learning. So till now, we have seen that in the incremental learning setup, you had a model, and you got it to train on one particular task, maybe which has 2 classes, and then you got another task on top of it that had another 2 classes, and you were then basically training them one after the other and not necessarily parallelly. Okay. There can be situations where you would want to train, you have a common data somewhere over here, and there are multiple tasks that needs to be performed by the same model on the same data. Maybe one task is for creating the classes, the other task is maybe to check whether any of the images contain a particular person who is smiling or not. Okay, another task may something similar, maybe counting the number of persons in that particular image. Okay. So you can have a lot of parallel tasks based on the same data, and it's been generally observed that if you train tasks on the same data separately, can compare it with a multitask learning setup where you have a set of initial layers that are shared and some final layers that are task specific, generally the performance on even some of the harder tasks improves. Okay, because you are training the model to come up with the best representation for a number of set of tasks, and as a result it starts to identify even better patterns within your input data. Okay, that's the general idea behind multitask learning. Okay, so the idea is that you want to find good classifiers or maybe good models for all of these tasks when you're training them simultaneously. Okay, and this will obviously will be useful only when these tasks will share some common factors of variation in the data. So as we had seen in the first class, every data will have some factors of variation which determine the different properties of your data. Some of the tasks may require one particular property, some other tasks might require some other property, but there will be some common properties that are used by a lot of the tasks. Okay. And if there are some such cases,
One thing, so how,
yeah,
on the which basis we will decide the task here? Task will be our final output, right?
task will be something like say a very basic concept is, suppose you want to predict the classes of a given setup, say you have car, dog and something, and another task is maybe check whether the object is rotated by some angle or not. It's a very basic form of multitask learning.
Mm-hmm.
Okay, so task is something that you're training your model on, so you already know what the task is. Maybe you have to train a model for that these multiple tasks.
Mm-hmm.
Okay. So one option is obviously you train these models separately. You train one model for simple classification, one model for rotation classification, and so on and so forth. And another option is a multitask learning setup where you share some of the initial layers and then you have a set of task specific layers and you train these tasks simultaneously on this data, on the same data.
Mm-hmm.
That's the
So that
general
you can achieve simultaneously many informations.
many information tasks. So it has multiple advantages. You are using a single model, so you're storing, you're saving at least this much of shared layers space when you're basically performing different tasks. Otherwise, if you had separate models, these portions would get repeated. So your computationally your storage requirement is reduced. Also, it has been seen in many cases when you train parallelly simultaneously multiple tasks, the generalization performance or the performance on each of these tasks also improves.
Mm.
Okay, so you have these benefits with multitask learning.
Thank you, sir.
What are the application where we might use such kind of model? Like, is it more robotic oriented application or?
Application, I mean, say suppose it's only a requirement, right? Suppose you want, say for example, for your robot only, you want to have one single model that identifies your if there is any obstruction in its path, and you also want to predict the distance. Okay, so you can have one classification model that predicts the obstruction and one regression model that might give you the distance from that particular task. Obviously, same model cannot do both of these things. So you parallelly same output head cannot perform both of these things. So you parallelly perform these two things. The other option would be to create one model that identifies obstacle and other model that finds distance to the obstacle. But then they are separate entities, so you require separate storage, separate training, and everything separate. And say on a very lightweight model, you want to reduce the amount of storage, reduce the amount of computation. So you might train a single model that performs multiple operations simultaneously. Okay.
Yeah. Okay. One more question, like how this is more different from the ensemble based, task learning where we have different ensemble models and for
So for
different tasks.
ensemble, you have the same task only, no? So you have multiple, say, models that predicts cats and dogs, and then what you do is that you take some average or voting decision to decide whether it's a cat or a dog. So task is basically the same for the ensemble.
Okay, so here we are differentiating between the tasks themselves.
Yeah, the tasks are different here in this
The
case.
model remains same.
The model,
The
at least
initial
the
layers, the
initial
initial
layers, yeah,
layers,
initial layers
initial layers
remains the same.
remain the same.
Uh-huh. Okay. So yeah, so the general approach is to use at least the initial layers as shared layers, because generally you learn more, say, generic filters in the initial layers compared to say your later layers, and then you have say task specific layers for each of the tasks, and they are sharing the same set of layers. So the representation learned is also much better. Okay, and we have also, I will describe why we are doing this all parallelly, because we have say computation requirement, or in some cases we have seen that multiple tasks
So
when
like
trained parallelly also gives
shared
better performance.
shared layer means they want to learn everything as a input, and after learning complete on shared layer, then they will divide the task specific filters like that, right?
No, 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 no. So basically what will happen is, suppose you have say three convolutional layers initially. You give an
Mm.
image as an input. You have three convolutional layers first, and the output of this convolution layers goes to two different heads. One is for say classification, other is for regression, and you train this entire thing simultaneously.
Mm.
So these set of layers will get loss or back propagation from both the classification loss as well as the regression loss. But this particular layer will only get the classification loss back prop, and this particular layer will only get the regression layer back prop.
Mm.
That's why this is called shared, because it is learning from both the losses.
Yeah, in shared zone, they
Huh.
have taking all the inputs, right? And
Yeah,
the
yeah. Input has to go through here only. No, these are the initial layers. Input has to go through here, and the output of this layer goes to the task specific layers.
Mm. Okay.
Right. Okay. Yeah, so this is something which I have mentioned, that when you learn multiple related tasks at the same time, it's been observed that it generally performs better even on, say, some of the harder tasks, which individually might be giving a lower performance, but in a shared setup, you tend to learn a more generic set of representation, and the performance has been seen at least in some of the harder tasks that also gets uh, better solved using, say, a multitask learning setup. So if you have, say, individual training models where you have say, separate models for every task, you will see that the losses for each of these tasks will basically affect all the layers. Say for your task 2, it will affect the final layer as well as all the input, I mean, the intermediate layers as well, separately if you're using separate networks. But if you have, say, a multitask learning setup where you have some shared layers and the other layers are some task specific layers, you will see that at least for the task specific layers, they will only function or they will get optimized based on their corresponding laws of that particular task. But the shared layers will get updated based on a combination of these losses. So you can also maybe determine through some validation what hyperparameter weights each of these losses you should give for training the shared layers. So you have your shared layers and you have task specific layers, and their backprops will depend on different types of losses. Okay, and this is a very, very
So,
basic example
one
which I just,
question.
yeah.
So here, like, if we perform the task one and getting the loss for that,
Uh,
so that loss is affect to the task two's loss.
no, no, no. It will not affect task two's loss, but it will affect the loss one will affect your shared layer. Okay, so all the losses will affect the shared layer. So this particular shared layers will get optimized in a way that is good for all the tasks. So the representation learning will be such that these representations are much more generic, so that you can apply it to multiple tasks. Individually, if you go to the task specific layers, the task specific layers will only be updated by their losses, corresponding losses. This will not be affected directly affected by the other losses. But indirectly, since your initial layers are anyways getting updated by all the losses, so indirectly you can say all of these tasks are uh, basically interconnected to each other through your shared layers. Right. So this is a very simple multitask learning setup where you are given any image and it has some associated class label with it. You rotate it by some particular angle, say 180-degree, and then you send it to a feature extractor. And the feature extractor will produce some embedding. This will be your shared layer, and that embedding will be passed on to a label classifier and a rotation angle classifier, and you predict the rotation angle, the prediction class and the rotation angle, and you basically train them. So this portion will be the task specific layer, and this feature extract will be the shared layer. And it's a very popular way of performing, say, incremental, not incremental learning, but multitask learning. And generally, this setup has been used as an auxiliary task. This particular rotation prediction has been used as an auxiliary task to improve the performance of the main task. So if you pick up any classification problem, especially if you're using natural images, if you can add this additional rotation based classification as an auxiliary task, you will see that the performance on the test set generally improves in that particular setup. It's been observed in a lot of scenarios, and this particular setup has been used therefore in, say, situations like, say, your few shot learning, your class incremental learning, a lot of setups, because in general such multitask learning setups act as an auxiliary task also in some cases, and it helps improve the performance on the main task. Okay, and this is something you can try out. I mean, it's not very tricky. You will just have to rotate your input image by a fixed angle and then use a rotation classifier to predict the rotation. Okay. Another option is that, I mean, you can, this is just a simple example where in some papers for medical imaging, they have also simultaneously performed, say, segmentation and classification based on the same data. And it's been observed that in this particular setup, the segmentation performance is generally better when you're, I mean, at least for the time when this paper came out. The segmentation performance actually improved when you performed a multitask learning combining, say, segmentation and classification. Again, the base set of layers will still be common, but you'll have some layers that are specifically meant for segmentation and other layers that are specifically meant for classification. Okay, right. So this is basically your different flavors of transfer learning that we have seen. And one term that gets often exchanged with the concept of transfer learning is the domain adaptation frame. And in some cases, it's also used interchangeably. Okay, but we'll look at one specific aspect of this particular setup of domain adaptation that makes it maybe slightly different from the transfer learning cases that we have seen. Okay, so in case of transfer learning, we generally consider that when there are two tasks, these tasks are different. Okay, but there are some common factors of variation which help maybe the other task from the given current task. Okay, and that's why we are able to transfer knowledge in some way from one set of tasks, model trained on one task, to a model that's getting trained on the other task. Okay. So in case of domain adaptation, we will consider that the task basically remains the same, but the input distribution will differ a bit. Okay, so you still have the same class, maybe you're still predicting cats and dogs, but suddenly, remember, I think someone had asked me in the previous class about an incremental learning setup where the classes don't change, but the data, we get more and more newer data. Okay, so this is somewhat similar to that, but in this case, your input distribution changes. And if your input distribution changes, you cannot directly apply your transfer learning to a domain adaptation setup, because what will happen is that, suppose you have trained your classifier to look at cats and dogs from the Indian subcontinent, and now suppose your new domain, you get data from, say, the African or the Egyptian cats and dogs, you'll suddenly see that your classifier that was working very well for these set of classes will suffering poorly for the cats and dogs from Egypt. So there is a difference in the input distribution. There is some shift that has happened, even though the overall task is still the same. Say, for in this case, it's still classification. Your input has become slightly different. As a result, your initially learned network that was performing so well will not be performing well anymore. So we need to adapt the domain basically on which your model is supposed to operate on, and so that your model can now perform well even for your target domain. This will not be a problem if you have enough data in your target domain. You can simply go ahead and train a good, I say, classifier in your target domain. But this will be a problem when you don't have enough data in your target domain and you want to utilize some of the information from your source domain to help learn a better classifier in your, say, target domain. Okay. And this is one example of this thing. Say, for example, you're doing a sentiment analysis and you have to predict whether a particular review is positive, negative, or say neutral. And suppose you have trained this entire setup using, say, reviews of, say, books, videos, and music. And suddenly you want to utilize the same model for reviews of some televisions and other products. It might be a bit tricky because some of the words or some of the jargons that you generally utilize for, say, books, music, and videos may not be relevant anymore for your television or other, say, electronic products. And as a result, even though the task is still the same, you're still predicting some sentiment. Your data, input data's general distribution has changed, and your model has to be then adjusted accordingly to your target domain. Okay. So the models trained on your source domain may not perform well on your target domain because your, say, your data distribution may have changed, which is something we just mentioned. Okay. And even though there are some maybe similarities between these two domains, for example, the classes are still the same. So we'll see some ways of performing domain adaptation. Okay. So there are different types of domain adaptation. We'll maybe look at some of them, not all, but let's see at least in terms of definition what these look like. So you have your supervised domain adaptation, where you have labeled data available for both your source and your target domains. Okay. And your objective will be to use your labeled source data to improve the performance in the target domain. Okay. While you're also utilizing the labeled data in your target domain as well. Okay. So you have data available that is labeled for both source and target domains. You have an unsupervised domain adaptation problem where you have labeled data only in the source domain and the target domain only has unlabeled data. You don't have any labeled data in your target domain. It might be a situation where maybe obtaining labeled data becomes very costly process. For example, suppose you are suppose there is a new disease that has come up and you have access to your access images, but this need to be annotated, and for annotation you require some medical expert to annotate these images, but then it will take time and it will take time. It might also cost you more because such people who are aware of this new setup may be few. Okay. So can you do something that even without annotating the data, and we are still able to perform, create a classifier or model for your new data as well, utilizing the previous set of, say, classes that you have. Okay. So for example, you're still predicting between, say, whether the person has pneumonia or not, but then with the advent of a new disease, the X-ray that comes up for this new disease that indicates pneumonia has become maybe slightly different now, and you still want to use the previous classifier or maybe update it a bit to work for the new model, but you don't have any labeled data for your target domain. So what do you? So that falls within the case of your unsupervised domain adaptation. Semi-supervised is a mixture of both of these things. So you have a small amount of labeled data and a lot of unlabeled data in your target domain, and in your source domain you anyways have your sufficient labeled data. Okay. So you'll have to utilize both your supervised as well as unsupervised techniques. Okay. And there can also be multi-source domain adaptation where you can have, say, multiple source domains and you want to basically transfer this knowledge to a target domain, a single target domain. Okay. So all of these cases covers situations of a sudden shift in your, say, distribution of your inputs, and you don't have enough data for you to retrain that entire model on the new domain. So you want to utilize the current domain in a way so that you can still perform these classification, whatever task on your target domain as well. And we'll look at one particular example of this particular setup, which is your supervised domain adaptation. And if you'll observe that the idea behind any of these setup is not very complicated. So generally, when you have your target data that has maybe differed a bit. So for example, this example is a case where you have, say, model images of your TV, laptop, and cycle, which you get on, say, your websites, your shopping websites. And your target domain are the actual photos that customers actually post on these review websites. Okay. Obviously, the ideal model images of the products will have, say, maybe no background and will be perfectly aligned to your camera and everything. And if you have trained a model based on that, and suddenly if I give you target images which has a lot of background clutter, which is on, say, the thing is on a road, there are also other objects within view, then your model will not perform that well because the input distribution has suddenly changed a bit. So what can we do in order to adapt your model to perform well in your target domain? Okay, so this is a paper that came in ICV 17, Unified Deep Supervised Domain Adaptation and Generalization. Okay, in this particular setup, they also make the problem a bit, more harder by saying that you have label data for both source and target domain, which is the requirement of a supervised domain adaptation setup. But the training data in the target domain is limited. Okay, which means you don't have an option of basically training a new model on just your target domain. Okay. So if there was no difference as such in the distribution, you could have directly trained the network on the source domain and evaluated it on the target domain. But this is not an option in this particular case. So you have to do some sort of an adaptation or say training of the source domain model so that it also functions well for your target domain. Okay. Now this is something we'll try to look at and what these authors have tried to propose as a solution to this problem. Okay. We'll see what can be done in this particular setup. Okay. What the general idea is that you need to do some sort of alignment of these, say, examples that you have, along with the examples that you had in your source domain. So you have TV images of TV in your target domain. You also have some model images of your TV in your source domain. We need to learn some sort of a common space. Remember CADA VE, we are learning a common space where similar objects get gathered together in the subspace, and dissimilar objects get shifted away from your common space. And we'll try to do something similar. Okay, the architecture will be a very straightforward one. You will have a feature extractor, okay, G, and you will have a classification layer, H. Remember, for your target domain, even though you have some label data, we cannot utilize this label data for this classification loss, because since you have very few label data, your classification loss will quickly overfit to this target data. So what this particular paper does is that it will use two different types of losses. One will be your classification loss. Another will be a combination of semantic alignment loss and separation loss. Okay. Your classification loss will only operate on images from the source domain, and your separation loss and semantic alignment loss will operate both on the source data as well as your target data. Okay. But you might say, then what's the use of having label data in the target? We'll see how to utilize the label data for these separation loss and semantic alignment losses. Okay. Right. The architecture, as I mentioned, will have a shared feature extractor that will be utilized by both the source data and the domain and the target domain data. And the classification module will be only used for classification for the source data. Now, we have basically three losses in this particular setup. We have the semantic alignment loss. So what it does is that it will ensure that the samples from different domains, say one in the source domain, say TV from your source domain and TV from your target domain, which basically have the same level. Okay. And so it will force that the feature extractor produces such a feature in each of these cases which are very close to each other in the feature space. Okay, if it's a TV, it should be close to each other. It doesn't matter if it's from the source domain or the target domain. Okay. The separation loss will do the opposite. The separation loss will take two samples from the same domain or maybe from different domains. So you have a computer and a cycle, and it will ensure that they are as far apart as possible in the representation space. So whatever features they represent, they should be very far apart. Okay, and this thing will be done for samples from different domain with different classes. Okay, I mean, you can also do it within the same domain with different classes. That is anyways get covered by your classification loss, but it will cover all cases. So different domain, different classes, same domain, different classes, but not different domain, same classes, because different domain, same classes have to be brought together through your semantic alignment loss. Okay, and finally your classification loss, which is pretty standard. It's simply, it will take your source domain data only and predict the class, and with the backprop you'll be able to change, basically learn your classification setup. Okay. And if you look at this particular image, it might appear to you that these two networks are separate, but actually you see this line connecting over here. This is actually the same network. They are basically showing that they are providing you source data once and target data once. So it's still the same network. You're sharing the same network between your source and target data. Only the classification module is dedicated to your source data, and there's no classification module for your target data. Okay, so these are the three losses that we use for this particular setup, and the total loss will basically be a combination of these three. Okay, and one problem that you'll have to deal with is that since the data is very less for your target domain data, even finding this semantic alignment loss and this separation loss will be a tricky operation. Because if you had enough data for target and source, you could have simply done a one-to-one mapping maybe. Okay, say you choose one image X and one image Y, and then you get some feature over here. You create pairs X comma Y and you get a one-to-one feature. And then you find the corresponding semantic alignment loss if they are from the same class, or the separation loss if they are from the different class. But in this particular setup, what will happen is that since the number of images in target domain is very less, so you cannot simply rely on, say, a random set of, say, pairs of images that you have built up. You'll have to do much better. So what you have to do is that you will take all the target images and create such pairs with all your source images. So as a result, even though this, say, target setup is very less, maybe you just have one image per class, you will create so many combinations with all of the source images that your data scarcity problem is, you're solving it maybe indirectly, you know. Okay, and finally you still have to apply these three losses: your classification loss, that is solely for your source data, and separation loss is semantic alignment loss. But this is, if you I think you should remember this, that this is a very good way of reducing a limited data problem, and preventing overfitting to, say, a very set of limited data. So you generally try to create such pairs with other data which is abundantly available with your, say, target data that is not in that large number. And this, since you're creating such pairs, this number of pairs will be a huge number, because at least X is plenty, and then these losses will not suffer a lot. You will still be able to perform well on this particular set. Okay, great. So okay, I mean, let's finish up to this point, and any doubts up to this point? Hello.
Yes, sir. Is there any book covering all these topics?
Actually, these things are published research papers, so you'll
Yeah.
not necessarily get them in a book, but you can actually refer to these papers. I've mentioned the name of the paper, the author, and where it's published.
Okay.
So you can refer to those papers. I am providing you a summarized version of these papers.
Yeah. Thank you, sir.
Okay. Fine. If there are no other doubts, then we can end today's session.
Thank you, sir. Thank you all.
Thank you.
Okay. Thanks.
Thank you, sir. Bye.